Okay, welcome back. This is lecture number 9. This will be a basic trigonometry review. Now, we don't need a lot of trigonometry for the kind of physics problems we'll be solving in this course. But to start with, let's just remind ourselves about some of the special properties of right triangles. And the first thing that should come to mind is that if I have a right triangle, denoted by this right here, then the Pythagorean theorem holds, which says that c squared is equal to a squared plus b squared. Right, so actually let me write that out graphically. What does that mean? That means that if I have a square side length A, and I have another square side length B, this is a tough one to draw, then the sum of the area of those squares is equal to the area of the square on the longest side, which is always directly across from the right angle. So this is Pythagorean's theorem. A squared plus b squared equals c squared. And maybe we'll just do a little example on this one. So let's let a be equal to 3, so b be equal to 4, and we'll let c be equal to 5. So let's just confirm that this is really a right triangle. We have 3 squared plus 4 squared equals 5 squared. Well, 3 squared is 9, 4 squared is 16, 5 squared is 25, and we see that 9 plus 16 is indeed equal to 25. So these side lengths are valid for a right triangle. That I would really call maybe geometry. So we haven't done the trigonometry yet. So what do we need from trigonometry? Basically, if we consider a right triangle, this time I'm going to label the sides a little bit differently. I'm going to call this longest side across from the 90-degree angle the hypotenuse. I'll just label it as H. I'm going to call this side, well, first I'm going to label this angle and call it angle theta. So I'm going to define the basic trigonometric functions in terms of this angle theta on this right triangle. We call the side opposite from the angle of interest the opposite side, OPP, and we call the side that is adjacent to that angle ADJ. Now, for a given triangle, like say the 3, 4, 5 triangle, the ratio of the opposite side to the adjacent side will be the same for similar triangles. So if I were to extend this out just a bit, that's a terrible line there. So if I can fix that. Like so. If this was originally 3, then this new side length would be 6. If this was originally 4, then this new side length would be 8. And so we'd have a ratio of 8 over 6, which is the same as 4 over 3. This we can write as 4 times 2, and this we can write as 3 times 2. The 2 and the 3, the two 2's cancel in the numerator and the denominator, and this is the same ratio. So this is the essence of these trigonometric relationships. And we can define some special functions. The sine of theta we'll define as the ratio of the opposite side over the hypotenuse. Opposite over the hypotenuse. The cosine of theta we'll define as the adjacent over the hypotenuse. And finally, the tangent of theta is defined as the opposite over the adjacent. This is also equal to, and you can show this algebraically, the sine of theta divided by the cosine of theta. These are the basic, really the two that we'll need the most are these guys right here, the sine and the cosine. And why do we need them? Because we want to specify stuff in terms of the angle. And we'll see that when we start talking about vectors in the next lecture, that we'll want to specify things in terms of, say, an incline. Say we're launching a cannonball. Instead of firing it straight ahead, we're going to fire it 30 degrees up into the air. That 30-degree angle we'll use to break down the velocity vector into its x and y components. So it's going a little bit in the x direction, it's going a little bit in the y direction. And so we'll use these trigonometric functions to do that for us. The evaluation of these, you can look up in a table, or you can use a scientific calculator to find the values for it. So if I were to type in, say, the sine of 45 degrees, my calculator would spit out for me the decimal equivalent of the square root of 2 over 2, for example. That said, there are a few basic angles that you'll want to remember, and I'm going to write them down right here. So if this is the angle theta, and I'm going to work in degrees. I know that people will talk about working in radians, and I'm not even going to really, well, I guess I could define quickly what the radians are. If we imagine that a unit circle has 360 degrees into it, then we can think that the circumference of a circle, you might recall, is equal to 2 pi times the radius. Well, if we let the radius be equal to 1, so we're talking about a unit circle, then the distance around that circle is 2 pi. That's the length. That's the circumference. So to equate 2 pi with 360 degrees gives you the relationship between radians and degrees. But I like to work in degrees because we think in degrees, not in radians. So let me just write the sine of theta, and also I'm going to give you the cosine of theta. If you need the tangent of theta, you can again take the ratio of the sine to the cosine, but I don't think we're going to have a lot of use for the tangent of theta in this course. So the first angle to consider is 0 degrees. Well, just imagine that this triangle had a 0-degree angle. Well, what would the length of the opposite side be? Right? Watch it as it walks down like this. The opposite side gets smaller and smaller and smaller, and it becomes 0. So the sine of theta, being the opposite over the hypotenuse, would be 0. The cosine, on the other hand, as the hypotenuse moves closer and closer to the adjacent line, these two become one and the same, and so the ratio of the two is just 1. So the cosine of 0 degrees is 1. The next angle to consider is 30 degrees, 45 degrees, 60 degrees, and then 90 degrees. And so I'm going to jump all the way to 90 degrees. That would be where the hypotenuse is angled up all the way to make a 90-degree angle, and you can see that the adjacent is now the side length that becomes 0. So it's the cosine of theta, which is 0 at 90 degrees. The sine of theta, on the other hand, the hypotenuse and the opposite side are of the same length, and so the ratio of those two is just 1. And so the sine of 90 degrees is just 1. Now with that said, I'm not going to show, derive specifically these three special angles in the middle, but I will give you a mnemonic to remember them because we'll use them all the time. And the mnemonic is 1, 2, 3. And it's 1, 2, 3, all over 2. So these three values in the middle, 45 degrees, which is 15 away from 30, and 15 away from 60. Right? So these are equal distance in the two different directions, increasing or decreasing the angle. And maybe if I wrote this a little bit neater, a little more space between it. So 1, 2, 3. You can always, and there's always a square root in the numerator, but the square root of 1 is just 1, so I'll eliminate that here. Now for the cosine of theta, it's exactly the opposite. It's 3, 2, 1. So square root of 3 over 2, square root of 2 over 2, and then 1 over 2. So you see there's this relationship between them. At 45 degrees, the sine and the cosine are equal, which makes sense since 45 degrees kind of bisects 90 degrees, and so you get an equal adjacent component and opposite component. There's just as much rise as there is run, if you want to think of it that way. So these are the basic angles that we use in the problems that we work. If we had occasion to do something that was a little bit strange, like say calculate the sine of 37 degrees, then you can use your graphing calculators to do that. I think that's pretty much all I wanted to say. Maybe just bring it back around to the Pythagorean theorem once again. So notice that we have that the opposite is the Well, if I write the Pythagorean theorem in terms of h, opposite, and adjacent, it looks like this. H squared equals opposite squared plus adjacent squared. And if I divide both sides of this by h squared, then h squared over h squared is 1. The opposite squared over hypotenuse squared, this is the same thing as opposite over hypotenuse quantity squared. And the same thing for the adjacent over the hypotenuse squared. But opposite over hypotenuse, that's just the sine of theta. Of course, this is squared. And the way we write that is like this. We put the squared sign right there. And the adjacent over the hypotenuse, well, that's just the cosine. And so I get the cosine squared of theta right here. And this is the equivalent of the Pythagorean theorem in terms of the trigonometric functions. The sine squared of theta plus the cosine squared of theta is equal to 1. So we've kind of come full circle, so to speak. And I think that's all we need to say about the basic trigonometric functions. We may use a trig identity here or there. I think we will. For the range equation, you can look these up in books. You've probably studied it if you took trigonometry or pre-calculus. But other than that, we're going to have we're going to have a lot of usage of the trig functions, but we will use the sine and the cosine pretty regularly, mostly in doing 2D kinematics.